As edge computing proliferates as a central feature of digital transformation, containerized OPC servers with automated orchestration have the potential to deliver a distributed, endlessly scalable framework. It's a model that enables rapid deployment, configuration, and centralized management. It has the potential to cut costs. It has the potential to cut the time it takes to add new data sources and add new endpoints on edge nodes, ensuring consistency, security, and seamless updates. ErgoTech is based on the Pajarito Plateau in Los Alamos, New Mexico. I'm Jim Redman. I'm the founder and president of the company. For a great many years, we've been delivering solutions to general manufacturing, but we've primarily focused on the semiconductor industry, delivering SexGem solutions in that space, notably a large number of SexGem to OPC servers and clients. Over that time, we've built specialized tools for semi, but we also have a general purpose IoT DX product. You can consider our MI Studio a combination of your favorite logic diagramming product and a drag and drop visualization builder. However, our focus is always on deploying applications as OPC servers. We've been delivering what would now be considered edge solutions on Linux since the late 1990s. The challenge there is we were constantly thwarted by the Windows-only OLE for process control. OPC UA brings us a whole avenue of cross-platform solutions with the ability to run those on edge and cloud platforms. But it's still predominantly run on Windows. It's still predominantly a Windows-based protocol. Containerization and edge deployment bring us some huge new functionality and some huge flexibility. We can deploy new servers quickly. We can deploy them with minimal configuration. They can be easily stopped, updated, and redeployed. And that allows for some new applications. We have self-contained data. We're running these right in the edge. We're running them as close to the sensor or the device as possible. So we're not relying on data coming across the network, which means we can start thinking about giving these solutions more autonomy. We can use that available data to make intelligent decisions, to make the true data-driven decisions at the edge that allow us to really benefit from this. And that includes the application of the huge new class of applications that are agentic AI. The challenge is that the tools required to deliver this functionality are still quite new to OT. I'm not convinced they're actually significantly more complex than the existing requirements. I mean, maintaining a monolithic OPC server and troubleshooting it is not a trivial project. It's just larger than new. And so as an industry, we need to try and bring that level of capability down to the OT environment. IT folk tend to assume that everyone understands what a container is and why they like them so much. You can kind of consider a container to be like a self-extracting, self-executing zip file. Except instead of having to go and find it on a shared drive, put it on a system, and hope that when you get it there, that system will support the executable and has all the correct libraries installed to do that, the deployment of a container can be automated. Containers in this case almost always mean Docker. Docker has become the standard for a container, so the Docker is kind of like a self-extracting zip. But they're way more self-contained, so they don't rely on the particular features of the operating system. They don't break on every OS patch update. If you want another way to look at it, you could consider them to be like a mini VMware platform or a VirtualBox if you're familiar with those technologies. So let's just quickly put together the components of a containerized OPC UA system. I've got some devices I want to collect data from. So what I need to do is I need to add an edge device. Containerized OPC servers are great. They can run in the cloud. They can run on servers. They can run on virtual machines. You can run them anywhere. But primarily what we're interested in doing today is putting in edge devices with OPC UA servers. So I get an edge device. The edge device already provides me with some security. It has a limited attack surface, so I can make it dual-homed and protect the devices that are behind it from the factory network and expose the data from those only in an OPC UA format. To do that, I add my Docker to the system. So now I immediately have OPC UA. And then, of course, to make it do anything useful, I need to tell it what it's talking to, what the devices are, and provide some diagnostics. So really, it's not that different from any other OPC UA system you're familiar with. It's essentially the same OPC UA functionality. The way it's deployed is a little bit different, but it's fundamentally something that should be familiar. In any digital transformation, the goal is to get more complete and more accurate data sets. That usually means bringing in data from systems that have previously been inaccessible, systems that have been siloed, or systems where other barriers exist to that integration. A containerized OPC UA server is an obvious application here. It can be spun up relatively quickly. It can be spun up potentially at a much lower cost than trying to modify an existing infrastructure. And multiple systems can be brought online to wrap and embrace legacy and other systems. It means that data can very quickly be made available to SCADA systems, historians, and other OPC UA clients. So most significantly, it increases the flexibility and it reduces the integration cost and encourages the removal of barriers and silos. We can consider Docker containers to be modular software building blocks. We're already committing to a Docker. We already have our OPC UA Docker running on our edge device. But that also means we can start to bring up other Docker containers. We know it's Docker capable. We can add other containers as our needs evolve. And it's fairly simple to spin up new containers alongside our existing Docker. Remember, they're containers. They're self-contained. One thing of note is that edge devices are increasingly becoming capable of artificial intelligence and machine learning applications with specialized devices like the NVIDIA-powered edge devices that have GPU capability built into them, and the AI chips are already built into those devices. Using that as our edge device, then we can start to look at putting some real intelligence on that device. And we can do that by simply adding a Docker that contains that AI ML intelligence and can access the data that's within the OPC UA server. That brings us a lot of advantages because once again, we're not relying on network loop, that we know that we have access to that data locally. We then have the potential to increase the autonomy of our edge device. We can start making data-centric decisions. We can then feed back directly from our edge device. And as we're seeing huge advances in AI applications, one of the biggest ones that was mentioned earlier is the whole growth of agentic AI, where we start using not just a single AI model, but potentially multiple models that can make decisions that a single model wouldn't manage to make. And we can give that system then agency because we trust the intelligence, the decisions of those models well enough to let it feed back directly into the process. We've been talking about really a single OPC UA server, but of course the power of the containerized and edge solutions is that we can scale them up. We can add additional edge devices as demand requires, and we can do that seamlessly. We can deploy, update, and replicate OPC UA containers without really impacting anything about the existing infrastructure. If you're going to start making critical decisions based on data, you need to be confident of the provenance of that data. You need to know where it came from. You need to know that it's accurate. You need to know that it's the correct data. The beauty of having OPC UA containerized servers close to the source of the data is that you get that level of confidence. You know the value contained in that OPC server is the value from the data source. There's no danger of ingestion pipeline errors. There's no danger of extraction transfer load, ETL errors that you missed. You can't have hidden network errors. If there is a problem with the network, you're going to see that immediately. You're not going to be able to connect to the OPC server. The further benefit is this is OPC. OPC has a very well thought out, very rich data model that guarantees you're going to get timestamps on every tag and guarantees you're going to get quality on every tag. So if there is a problem with that data, you will immediately be able to recognize that there's a quality problem. You'll know immediately that there has been something that's gone wrong. It's lost connection to its data source or whatever other error has occurred. You'll get that directly. So if you get error-free data from the OPC server, it's authoritative. It is the ground truth. So we can browse our OPC server and discover available tags from the OPC server directly. We have metadata associated with each of those tags, so we know at least some information about every tag that's in the server. There's no ingestion pipeline, so there's no chance of stale tags. In the case of a stale tag, you get a subscription error. And the OPC server is the source of truth in a standardized form with metadata and context. These features avoid many of the problems of broker-based architectures. The broker inevitably has a copy of the ground truth. There's an ingestion pipeline that delivers that data to the broker. And so there's a risk that that ingestion pipeline will fail. There's a risk that that ingestion pipeline will fail and you won't notice that it's failed. Broker-based systems require really strict governance if they're going to avoid becoming a data swamp. They need really good discipline. They need really good design. And that's actually not trivial. The OPC Foundation got criticized for as much time as they spent on getting the model correct for OPC UA. Trying to replicate that in a JSON format or in some format from a vendor in an MQTT server or something similar is not guaranteed to get you the results you like. The number of times I've seen data that's in JSON format that's missing timestamps and missing per tag timestamps, that's missing quality, so you have no idea whether that data is good or bad, is far too frequent. At the same time, there is a huge attraction to having a centralized messaging hub. The problem with the architecture we've described for OPC and distributed OPC is there's no immediate way to know all the available OPC servers on the network. There's no way to discover those. OPC does have some networking discovery capabilities, but they're, say, infrequently implemented. So there's a huge attraction to being able to connect directly to a local broker to say, hey, this broker has all the information I require. So it's a trade-off. You have easy access to data, the provenance of which you cannot be totally sure of, or you have access to the OPC data that is the clear ground truth for the information you're looking for. So we have a number of approaches to avoid the problem of needing to discover and connect to all the distributed systems. I sort of hate to mention this in an OPC talk, but there are other IoT protocols, and since we have a Docker container, there's nothing to stop us putting those protocols in a Docker container in parallel with the OPC UA server. So we can feed OPC UA server to SCADA, to historians, to anybody else who wants to be an OPC UA client. At the same time, we can be pushing data through Sparkplug or MQTT to a UNS or to the cloud or anywhere else through any other protocol. That's just one of the benefits of having building blocks that we can just build up systems with using Docker. We can also stay completely within the OPC ecosystem and use an OPC aggregator. An OPC aggregator kind of gives us the same functionality as a local broker in that it will collect data from all the various distributed OPC servers and make that available either as OPC or in some other format from a single location. This has a great many benefits. I mean, it kind of, at some level, it sort of looks like a broker system, but again, the beauty of it is that we know the provenance of that data. We know that data is OPC data. We know it has timestamps. We know it has quality. We know it's been well thought out. So there are clear advantages to the aggregator as an OPC. Another technology that can help us here is the OPC UA pub/sub standard. That's covered by a 2024 video by Randy Armstrong, but that really lets us integrate OPC data well into a UNS or an MQTT system. We can add that as a separate Docker in the same environment, or we could simply add it as part of the Docker that contains OPC UA. There's a fairly recent development in data architectures that aims to some degree to solve both of these problems. The data mesh architecture is an approach, it doesn't have a prescribed implementation, so it doesn't tell you how to implement it, but it does require that there be governance of the system. It does require that you have domain experts who create data products. And so you avoid the possibility of it devolving into a data swamp because you have people who are responsible for delivering that data. The idea of data as a product. The goal here is that the data not be copied from the data products. The idea is to produce a data virtualization layer. One approach to that is to use GraphQL as a data virtualization layer. GraphQL is federated and distributed, which means the federation means that the consumers of the data ask a single local data source similar to a broker for the data they need. The data is not stored in that server. That server will create queries that will go out and get that data from the distributed system. So there are no copies of the data. The data you know you're going to get is a ground truth. It provides the benefits of a broker in terms of ease of use, and it provides the ground truth assurance that comes with not copying data. If you're really interested in modern data architectures and the data mesh, I highly recommend following the work of Zhamak Dogani. So we've seen the potential benefits of containerized OPC UA in terms of flexibility, the potential for cost saving. In order to achieve those, though, we need a strategy to get the Docker containers to get the OPC servers deployed rapidly and conveniently. The requirements are actually quite simple. For a no-touch deployment, what we want is when the edge device powers up, it's going to go and find an OPC server image in the Docker registry. It's going to pull that image and the configuration for its image from that container, launch the container, and so start the OPC server. It sounds at some level quite complex, but in fact, because Docker is standard and because a lot of people are dealing with Docker containers, there are actually some fairly good tools to make this happen. Which one is best for you depends on your organization. I mean, the easiest one for sure is to outsource this. There are a number of edge providers who will deliver no-touch deployments. They have excellent support at scale. The challenge, of course, is vendor lock. It's also my experience that those systems are not as OT friendly as you might hope, and so you can reasonably expect to need the vendor support, continuing support to deploy the system. If you have a friendly IT department, if you've managed to cross the OT-IT divide, the IT department are quite likely familiar with and enthusiastic about container technology. So it's quite possible that a local IT department will be able to help you with this, will be able to achieve this goal of no-touch deployment fairly easily. And it might be something they're fairly willing to do because it's something that potentially is more interesting in the task they have to do on an everyday basis. That also gives you internal control. It also means that if you decide that you need other containers for any other reason, the AIML containers or containers to connect to other systems or whatever you need, they would at least be familiar with that technology. That said, the requirements to deploy this are actually fairly well understood, and it's possible to bring those down to an OT level where a prepackaged OPC server can be delivered to the edge device without too much complexity. The solutions are all fairly open, they're all fairly extensible. They are new to most OT people, but as I say, I doubt they're that much more complex than maintaining a monolithic OPC server. They're just different concepts. Some of the ideas involved in this involve things that are already familiar to OPC UA users, things like validation using certificates. And so it's not unbelievable that an enthusiastic OT person, especially if you're not looking to deploy thousands of these across multiple sites, it would be well within reach of that person. Kubernetes is likely the most widely used orchestration approach for Docker containers. It's almost certainly the technology that's under the hood of most of the edge providers, and indeed, it's one you'd probably want to see there. It's an open source system that's had a lot of eyes inspecting it, and it's more secure than most custom systems would ever be. It's also extremely capable, which is both good and bad in our case. What we really need is to reduce some of this complexity to the level where we can deploy our simple OPC UA Docker containers in an air-gapped environment with as little support from the outside world as possible. I mean, we're looking to get this down to an OT level, so we want a local registry. The registry for a Docker container is kind of like the shared file system that we used to pull exe files from. If we can get to that level, the Kubernetes easily provides the capabilities we need to authenticate against certificates, to provide automated enrollment, to provide the automated deployment that we're looking for, the full zero-touch installation and updates. It also provides the ability to do health checks on the containers. In our case, we always want to do OPC UA health checks. We don't have much variation here. And with that health check, we can also restart the container on a failure. So what we're looking for in Kubernetes term is a simplified version of the control plane. Just to provide some idea of what that simplification might look like. We know we're only looking to deploy our OPC servers, and frankly, realistically, with this level of orchestration, we're really looking to deploy them at moderate scale, say hundreds, certainly not thousands, which means we can combine our control plane, the Kubernetes controller along with our local registry. Remember, the local registry is really just a file system of containers. And we can focus on configuration that's based on OPC and monitoring that's based on OPC. So this also brings us within the firewall, so we can deploy our local registry and Kubernetes control plane within a fairly small device, within a small server, a VM, or an edge device, and generally work towards bringing this down to an OT level capability by limiting the functionality that's available, but maintaining the essential features we need for no-touch deployment. So we've seen the potential for containerized OPC UA, the ability for it to decrease the cost and time required to deploy new data sources, the potential ability to wrap legacy systems, and also the ability to introduce new applications like agentic AI on the edge. The challenge of deployment is mostly just lack of familiarity with OT, and we need to do a better job of making sure that we simplify scalable deployments on the plant floor. Thank you, and please feel free to contact me with any questions or comments.